and welcome to the second lecture of module 5 for our computational techniques course. What we are doing in module 5, the first part of the module 5 is to look at various methods for doing regression. We started off with linear regression with one independent and one dependent variable. So we wanted to get a straight line of the form y equal to a0 plus a1x, where a1 is the slope of the curve and a0 is just the y-intercept. Okay, that is the model that we wanted to fit to a data set given to us xi yi from I going from 1 to n. What this representation means is essentially we have the data x1 y1, x2 y2, x3 y3 and so on up to xn yn. In this particular data we have defined our x1 as the independent variable and y1 as the dependent variable. The error we have defined as the actual value of the data yi minus the value that we get from the model by substituting a0, a1 and xi value over here. This particular model prediction so this is our model. When we substitute the value of xi in this model, the value of y that we get is nothing but yi hat. So yi minus yi hat term is the error term ei. Okay, so the objective in linear regression, or for that matter in any regression, is going to be to minimize the sum of square of errors. How do we define error is essentially going to be important, and we will look at that when we talked about advanced parts of, when we come to advanced parts of regression. But for now we will just minimize the sum of squares of error between the true value y and the model prediction yi hat. In order to minimize the sum of square of errors and to find a0 and a1 that minimize the sum of square of errors, what we did was we took this SE, we call this SE to represent sum of square of errors, and we differentiated it with respect to a0 and substituted that equal to 0, and then differentiated with respect to a1 and then substituted that equal to 0. That gave us two equations and two unknowns. We solved those two equations and two unknowns and we got the value of a1. The value of a1 that we got was summation xi multiplied by summation yi minus n times summation of xi yi divided by this term minus this term. That was the value of a1 that we got, and this is the value of a0 that we obtained. So this is pretty much what we did in the first lecture of module 5. What we will start off today in this particular lecture is take this example, the example of the 6 data that we looked at in the first module, and get the value of a0 and a1 to fit that particular data. That is what we will do first, and then we will go on to regression in linear regression in multiple variables, and then look at functional forms and so on and so forth. Okay, so let us now go and look at Microsoft Excel. Okay, so what I have done over here is the data that we had previously. So this particular data I have just taken that in Microsoft Excel. So this is our x, this data is our y. Okay, and on the board we had derived the value of a1, and the value of a1 that we had derived was basically summation x summation y minus n times summation xy divided by summation x squared minus n times summation x the whole squared minus n times summation x squared. Okay, and likewise we had derived basically the equation for a0 as well. A0 was y average minus a1 times x average. Okay, so this is the data that is given. So what I will do is I will just get the summation of that data. So I will write that equal to sum, and so what I have done is I have used the cursor keys to take the blinking rectangle over here, and now I press the shift key and use the cursor key to take the rectangle upwards, and then complete the brackets. Okay, so closing the brackets we will get the summation that we see over here. Okay. Okay, I have just moved the A0 down so that we get more space for doing our stuff. Now in order to get summation of yi, we will just drag this particular cell over here, and if we press F2 key we will be able to see that this particular guy is nothing but summation of yi. Okay. What else do we need? We need summation of x, summation of y that we have already obtained. We need summation of xy and summation of x squared. So what we will write over here is xy and we will just increase the font, change the font to Times New Roman. Okay, and this becomes our xy, and likewise we need x squared. And we will just use a superscript so that it just looks good. Okay, so what we have over here is okay, so we will calculate xy, which is nothing but the product. Okay, I will increase the font size so that it is visible for all of us. Okay, so xy is nothing but equal to x star y, that is going to be our xy, and we will just drag and move and drag this for the entire column, and our x squared is going to be equal to x caret 2. X is this particular cell, the caret sign is the power sign, and 2, that is going to be our x square, and then we can drag and drag this for the entire column, or we can just double click it and it will get dragged itself. Okay, and then we want to find out summation of xy and summation of x squared, and for that we will just copy this and then control C and control V over here, and we can just press F2 to verify what that is. That is nothing but summation of this particular column, which is summation of xy, and this is nothing but summation of x square. So our value of A1 is going to be equal to summation of x multiplied by summation of y, that is going to be equal to, we will start the brackets for the numerator, summation of x multiplied by summation of y, okay, minus n. Now n value is 6, minus 6 multiplied by summation of xy, which is this value over here, and I click over here, and this is our numerator slash to represent division, and our denominator is summation of x squared, summation of summation of x the whole squared. Summation of x is nothing but this guy whole squared minus n times, which is 6 times summation of x squared, okay, and summation of x squared is this, and we close the bracket, and that becomes our denominator, and this is nothing but our A1. A0 is going to be y average minus A1 times x average, or this can also be written as summation of y minus A1 times summation of x whole divided by n, okay. So y average is nothing but y summation of y divided by 6 minus A1, which is this value, multiplied by summation of x divided by 6, okay, and that is going to be our A0, okay. So what we did, just to recap, what we did is we were given the data x y, that is over here. What we did in this particular case is found out the summation of x, found summation of y, then computed x multiplied by y over here, for each of these cases. So if we just take any cell and press F2, we will be able to see the formula for that cell. Formula for that cell is the blue colored cell multiplied by the green colored cell, which is nothing but xi multiplied by yi, or x4 multiplied by y4 in this particular case. This is nothing but x4 squared. We can see that when we press F2 key, this is F4 squared. Okay. And finally, after calculating xy for all of the 6 data points and x squared for all of the 6 data points, we get summation of xy and summation of x squared. If we press F2, we will see that is what we get over here, and likewise this is summation of x squared is what we get over here, and then we can substitute this. So what I am going to highlight over here is our numerator. Our numerator is summation of x, which is this guy, multiplied by summation of y, which is this guy, minus 6 times summation of xy, minus 6 times summation of xy, which is this guy. Okay. And if you look at the cell number, it is D10, that is our summation of xy. Okay. That is our numerator divided by the denominator. Okay. And that is how we get our A1, and likewise we can just easily get our A2 as well. Okay. If we go back to our regression that we obtained earlier, we had said y equal to 0.45 plus 0.47 x. Essentially, if we are going to truncate these particular values only to 2 decimal points, that is what we approximate value of our straight line we get as. Okay. So what we will do is we will just plot this data x versus y. So we will highlight all the data, click on insert tab, on scatter, and then we will plot using the scatter function, and this is going to be our original data. Okay, this is our x versus y data, and then we will get y hat okay. Y hat we said was nothing but A0 plus A1x. So we will again go to full screen. Okay. Y hat was equal to A0 plus A1 multiplied by x. Okay. And this is the first y hat that we get. What we actually need to do in order to drag and drop is just, we do not need a y hat at each and every point, but what I will do over here is in any way just get this y hat at each point. So I will give this delta. What delta does in Excel, what this delta does in Excel is when I drag this particular column downwards, okay, this particular E and 14 will not change. So I will just demonstrate that to you. Okay. So let us say when I just drag this down and do F2, instead of E16 and E14, it has changed to E17 and E15, because of which we get the value as 0, because E15 has nothing and E17 has no value over there. Okay. But now instead, when I include this dollar signs in Excel, okay, and then I drag this, just see what happens. If I do F2 over here, the value within the dollar sign has not changed, only the cell values over here have changed. Okay. That is what has happened. If we look at this particular expression, it is $E$16 plus $E$14 multiplied by A3, and the next expression is $E$16. See, this particular value has not changed, this particular cell value also has not changed, only thing that has changed is from A3 we have gone to A4. Okay. So that is what we will consistently be able to do for the entire cell. And now what we need to do is we need to plot, essentially we need to plot our, now I will change this font size also to 16 so that it is more visible. Okay. Yeah, and now I will plot this x versus y hat also in that data. We can do that by select data, click on add. Okay. The series name is going to be y hat. Okay. Series x values are going to be these values, and series y values are going to be our y hat values. Okay. And that is going to give us this red data, and we will basically do format data series and add a line over here, solid line with red color. Okay. So, this particular line represents our y hat, the blue data points over here represent our y, and the red data points over here represent our y hat. So, the red data points are y hat, the line is y equal to a0 plus a1 x, and this distance is our E3, this distance is E2, E1, E4, E5 and E6. Okay. So, this is the best fit line, best fit straight line we get, which passes through this the straight line that best fits the 6 data points that we had over here. Okay. And I had already done that before, and this was the best fit the line that I had obtained. Okay. So, this is how you are going to do your linear regression in a single variable. Now, let us go ahead and look at how to go ahead and do linear regression in multiple variables. Okay. And what I will do is, just for notational simplicity, rather than confusing ourselves with x1, x2, x3 and so on, I will just take the independent variables as x, u and w, and the dependent variable as y, just for the sake of simplicity. So, the data that we will have okay, x, u and w are our independent variables, y is our dependent variable, and the data we will represent in terms of xi, ui, wi semicolon yi, where I goes from 1 to n. Okay. The model we are interested in obtaining, the linear model that we are interested in obtaining, is going to be equal to yi equal to a0 plus a1 xi, or sorry, the model is going to be y equal to a0 plus a1 x plus a2 u plus a3 w. Okay. If we have additional variables, say v, m, p, q, it will be a4 multiplied by v plus a5 multiplied by m plus a6 multiplied by q, so on and so forth. There is no restriction on the number of variables we might be able to have in our model. The number of variables that we have in our model is predicated by the functional form of how many terms does the independent variable y depend on. Okay. So, the model that we are interested in finding obtaining is this. The error ei is going to be nothing but yi minus yi hat, which is nothing but yi minus a0 plus a1 xi plus a2 ui plus a3 wi. okay. This is going to be our error, okay, and the aim in multilinear regression or objective of multilinear regression such that we minimize the sum of square of errors. Okay, or in other words, okay, and this particular term we will call this as SE, just as before, okay. So in order to find the values of A0, A1, A2 and A3, what we need to do, we need to follow the exact same procedure that we followed earlier. We need to differentiate SE with respect to A0, differentiate SE with respect to A1, with respect to A2 and A3, and equate each of them as 0, okay. So what we will have to do is dou by dou A0 of SE by dou A1 of SE and dou by A3 of SE, okay. So this is going to be, now keep in mind that we take the summation sign, the partial differentiation will go inside the summation sign because the differential operator is a linear operator, and d of f squared. So let us say there is a function f, then d by dx of f squared is going to be 2 times f multiplied by df by dx. So we will use essentially this property in order to simplify our life. So what we will get over here is d by d of this particular term with respect to A0 or A1 or A2 or A3 is going to be nothing but twice this particular term, that is twice f multiplied by df by dx. df by dA0 is minus 1, df by dA1 is minus xi, df by dA2 is minus ui, and df by dA3 is minus wi, okay. So that is what we are going to get over here. So we will have summation I equal to 1 to n outside, we will have 2 times f, or in this particular case 2 times ei, 2 times yi minus A0 xi minus A1 ui, not A0 minus A1 xi minus A2 ui minus A3 wi, this multiplied by df by dA0, this particular guy is f, so df by dA0 is nothing but minus 1, so multiplied by minus 1 equal to 0, okay. We can delete the 2 and the minus 1 throughout, and essentially we will get the first equation as this equals 0. The second equation is going to be summation I equal to 1 to n 2 times yi minus A0 minus A1 xi minus A2 ui minus A3 wi, okay. This multiplied by partial differential of this term with respect to A1. There is only one term with A1 over here, and that is this term. So this will be multiplied by minus xi equal to 0. Again we can delete this 2 and we can delete this minus sign, and this is going to be the expression. Likewise, we will have the expression for this as summation I equal to 1 to n E multiplied by in this case ui equal to 0, and in this case we will have summation I equal to 1 to n E multiplied by wi equal to 0. Okay. We can take all of these guys on to the right hand side. So and essentially what we will end up getting is we will end up getting 4 equations in 4 unknowns. I will just write down the first equation, and based on that you will be able to write down all the 4 equations also. The first equation, if you look at this particular equation over there, we have taken all of these to the right hand side. So what we will get is summation I equal to 1 summation I equal to 1 to n yi is going to be equal to a0 multiplied by summation of 1, summation of 1 is nothing but n, a0 multiplied by n plus a1 multiplied by summation xi plus a2 multiplied by summation ui plus a3 multiplied by summation wi. Okay, this is going to be our equation 1. We will just do this equation also, and that we will call that as equation 2, our second equation. I will just erase this particular equation from here. Our second equation is going to be summation I equal to 1 to n. Okay, yi multiplied by xi will come over here. Summation xi yi is going to be equal to, all these terms will be taken to the right hand side, and we will have a0 multiplied by xi, summation from I equal to 1 to n, a0 can come out of the summation sign. So it is a0 summation xi plus a1 multiplied by summation xi squared, or summation xi plus a2 times summation ui xi plus a3 times summation wi xi. That is our second equation. So our first equation is yi equal to a0 n plus a1 summation xi plus a2 summation ui plus a3 summation wi. That is our first equation. Our second equation is I equal to 1 to n summation xi yi equal to a0 summation xi plus a1 xi multiplied by xi, ui multiplied by xi, wi multiplied by xi. The third equation is going to be yi multiplied by, I will just write it in the other sequence, instead of xi yi I will write it as yi xi. So just for consistent notation. So I equal to 1 to n, yi multiplied by ui is going to be equal to a0 summation ui plus a1 summation xi ui plus a2 summation ui squared plus a3 summation wi ui, and then the fourth equation. So now we have 4 equations in 4 unknowns, and the 4 equations in 4 unknowns we can write them down in this form, in the matrix form. Okay. The first equation is summation yi, the second is summation yi xi, the third is summation yi ui, the fourth is summation yi wi, and you can continue this further if there are more independent variables, is going to be equal to, and we have this A matrix multiplied by our A0, A1, A2, A3, okay. And if you are not yet comfortable with the way we have obtained this particular matrix form, I suggest you can go back and look at the videos of module 2, and essentially the lectures 2 and 3 in module 2 are going to cover how we can put these multiple equations in forms of this sort, okay. So we have summation xi, sorry, we have n summation, the first term is going to be n, then we will have summation xi, summation ui, summation wi, okay. Over here we have summation xi squared, okay. Next we will have summation ui, summation xi ui, summation ui, summation wi ui, okay. Keep in mind the pattern that is forming over here. This is summation of 1, which is n, this is summation of xi, summation of ui, summation of wi, this guy is summation of xi, summation of xi xi, xi ui, xi wi, ui xi, ui wi, wi xi, wi wi. It follows a consistent pattern, which that pattern you can keep continuing if you have multiple variables, and the same type of expression you will get in n equations and n unknowns also. So okay, and now we can use any of our methods such as say Gauss elimination, okay. So we can use Gauss elimination or any other appropriate method to get A0, A1, A2, A3, or if we have even more independent variables A4, A5, A6 and so on and so forth. Now this is one way of doing the linear multilinear regression. Another way of doing writing the multilinear regression is using the matrix method. Okay, let us look at the problem in just two variables x and y, and then we will extend it to multiple variables. We have the data data is x1 y1 and so on up to xn yn. We are interested in fitting the curve y equal to a0 plus a1x, okay. So the true data is going to be yi equal to a0 plus a1 xi plus ei, okay. So this we can write this as y1 equal to 1 times a0 plus a1 times x1 y2 is 1 times a0 plus a1 times x2, or more appropriately we will put the hats over here. Y3 hat is 1 times a0 plus a1 times x3, or more appropriately I think to write it in a consistent form is x1 times a1, x2 times a2, x3 times a3. It is the same term. Instead of writing as instead of writing this as a1 x1, a1 x2, a1 x3, I have written as x1 a1, x2 a1, x3 a1, okay, and so on up to yn hat is going to be equal to 1 times a0 plus xn times a1, okay. This in the matrix form we will be able to write this as our matrix y1, y2 and so on up to yn. This is going to be equal to, okay, 1 1 and so on up to 1, x1, x2 and so on up to xn multiplied by a0, a1, okay. That, so y hat is equal to this, y is going to be equal to plus the error terms e1, e2 and so on up to en, okay. So this is essentially what we are going to get, and the shorthand notation of writing all this is y equal to capital X multiplied by phi plus E, and the least square solution okay. This is the least squares solution for the problem as we had written y equal to x times phi plus E, okay. For example, if we have two equations in two unknowns, then x transpose x is so x transpose x inverse can be written as x inverse multiplies by x transpose inverse. X transpose inverse multiplied by x transpose is going to be identity, and for two equations and two unknowns we will get this as x inverse multiplied by y. If you recall from the previous lectures on Newton-Raphson's method, we had said that this particular type of an idea can be used in what is known as the Leuenberger-Marquardt method for finding out the solutions. This indeed, if with the same modification as we talked earlier, becomes the Leuenberger-Marquardt method for finding out the least squares. This LM method is usually not required in linear least squares problem, but in non-linear least squares problem this LM method becomes very useful. So for an equation y equal to x times phi plus error E, the least square solution that minimizes the sum of square error is given by this particular equation, and that is independent of the size of x and the size of y, okay. So now let us extend this particular problem to multiple independent variables to find y as a function of multiple independent variables. So, if the model that we were interested in is y equal to a0 plus a1x plus a2u plus a3w, okay. If this is the model that we are interested in, then our data can be written as yi equal to 1 multiplied by a0 plus xi multiplied by a1 plus ui multiplied by a2 plus wi multiplied by a3 plus the error ei, okay. So, yi in other words can be written as 1 xi ui wi multiplied by a0 a1 a2 a3 plus ei, okay. So, the least square solution again for this particular type of a problem is going to be x transpose x inverse x transpose y, where our matrix y as before is nothing but y1 y2 and so on up to yn. Now, the question is, how will the matrix x change? Previously what did we have in matrix x? We just had 1 and x1. So, the first column was 1 1 1 1 1 1 n number of times, the second column was x1 x2 x3 up to xn. Now, with 1 xi ui wi, the overall matrix is going to be 1 1 1 1 n number of times in the first column, x1 x2 x3 up to xn in the second column, u1 u2 u3 up to un in the third column, w1 w2 w3 w up to wn in the fourth column. Okay, and that is the result of the multilinear regression when we look at the entire problem using the matrix notation, okay. And the advantage of this matrix notation over any other method is that this is an extremely general method, irrespective of what the value of n is or how many number of independent variables that we have in our system. This method can be in a fairly straightforward way extended to this to any number of independent variables, okay. So, that is essentially what we have with respect to multilinear regression. What we have covered in today's lecture is we started off with linear regression and recapping what we did in the previous lecture, and this is what result we had derived in the previous lecture. And what we said is an alternative way of doing this is using the matrix notations, and in the matrix notations the alternative way was with y represented as y1 y2 up to yn, x represented as 1 1 1 and x1 x2 up to xn for linear regression in single variable, and the phi least squares was obtained from this particular solution. For the multilinear regression case, the X matrix in general will have a structure of this particular form, the Y matrix will have the same structure as before, and A0 to AN we can get, or A0 to AM we can get as phi least squares, again using the exact same equation as before. Okay. Before we went on to the multilinear regression using the vectorial notations, what we did was we covered the multilinear regression using the same method as minimization of the function as summation of SE. Okay. And the minimization of the summation of SE resulted in essentially M equation in M unknowns. For example, we have when we have the independent variable as X, U and W, we will essentially get the 4 equations in 4 unknowns. The 4 unknowns are A0, A1, A2 and A3, and then we can solve this equation using any of the linear algebra techniques that we have learned in module 3, and we can get the solution of the various parameters that we are interested in. So this is what we have covered in the first 2 lectures of module 5. In the next lecture, what I am going to cover is what is known as functional regression, which is essentially, instead of having a multilinear regression in variables like X, U and W, what if we have some kind of a functional form. An example of that, as we saw earlier in the first lecture of this module, was the specific heat can be written as some A0 plus A1T plus A2T squared plus so on. That is one example. The other example we had seen earlier is, what if the rate of reaction is written as K0 times e to the power minus E by RT, how we can convert it into linear case. We will not just tackle this particular example, but we will consider a couple more examples where we can convert this particular functional form into linear regression or into linear regression in multiple variables. And once we reduce it to a convenient multi regression form, we can then use any of the multi regression tools that we talked about today, either using the matrix method or using the method that we talked say 20 minutes earlier. Using either of these methods, we can get the value of A0, A1, A2 and so on. That is what we are going to cover in the next lecture. Okay. Thank you and see you later.